Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Hi, integration is the heartbeat of calculus. It's the tool we use to find everything from the area under a curve to the volume of a sphere or even the mass of a complex 3D object. But I know it can be intimidating, especially when you move from simple power rules to the world of triple integrals. That's why I've created this masterclass. I've compiled my entire integration library into one definitive series. We're going to start with the fundamental theorem of calculus to understand the why behind integration. Then we'll master the essential techniques, substitution, integration by parts, and partial fractions. But we aren't stopping at the algebra. I'm going to show you how to use these tools to derive the formulas for the area of a circle and the volumes of cones and spheres. We'll then push into multivariable calculus with double and triple integrals and finish with Simpson's rule for numerical approximation. Whether you're a high school student, a university engineer, or just someone looking to sharpen your math skills, this video is your complete roadmap. Use the timestamps in the description to navigate between topics as you study. Let's get started. The second part of the fundamental theorem of calculus tells us that if we have a definite integral over the closed interval AB, so that's the integral from a to b of f of x dx, then we can find the area under the curve, so the area shaded here in red, by subtracting the antiderivative of f of x, that's capital F evaluated at a, from the antiderivative, capital F evaluated at b. Remembering here that capital F prime of x equals f of x from the first part of the fundamental theorem of calculus. To prove this, let's define function g of x to be the integral from a to x of function f of t dt. Function g of x is therefore an antiderivative of the integral of f of t dt between these limits. We also know that many antiderivatives exist for a function. So let's say we have another function, capital F of x, which equals g of x plus c. To see why this is true, let's assume g of x equals x cubed divided by 3 plus 5. If we take the derivative of this, we get x squared. Now let's assume capital F of x is g of x plus 2. So substituting for g of x, that's x cubed divided by 3 plus 5, we get x cubed divided by 3 plus 7. So its derivative, capital F prime of x, is also x squared. So the value of c, shown here in this case, is 7 minus 5, which equals 2. Knowing this, we can say the function capital F evaluated at b minus the function capital F evaluated at a is the same as g evaluated at b plus a constant minus g evaluated at a plus a constant. So the constants c here and here cancel out, and this leaves capital F of b minus capital F of a equal to g of b minus g of a. We know from above that the function g of x is defined as the integral from a to x of f of t dt. So it follows that the function g evaluated at x, where x equals a, is the integral from a to a of f of t dt. So when evaluated, this is the function g of a minus the function g of a, which is 0. Intuitively, we are looking at the area under the curve at x equals a, highlighted on the sketch here, and evaluating the area, which is obviously 0. So we're therefore left with the function g evaluated at b is equal to the function capital F evaluated at b minus the function capital F evaluated at a. So evaluating our function g at x equals b, this will give us the integral from a to b of f of t dt. And we also know that the function g evaluated at b is equivalent to the function capital F evaluated at b minus the function capital F evaluated at a. Finally, if we replace our dummy variable t with x, we finish the proof, which shows that the antiderivative capital F evaluated at b minus its value when evaluated at a is equal to the integral from a to b of f of x dx. We saw in a previous video how the area under a curve could be sliced up in the x direction to create rectangles, and the rectangles then summed to find the area under the curve. We also saw that as we used more values of x, and therefore more rectangles were created, we had a better approximation of the area under the curve. We then went on to show that this process of finding the area under the curve was called integration. Integration is the reverse of differentiation, or the antiderivative. So for example, if dy by dx is equal to 2x, what is y of x? We're asking what function when differentiated gives us 2x. In this case, y of x is equal to x squared plus a constant c. So why is there a constant c, I hear you cry? The constant c is very important because there are many functions whose derivative is 2x. Let's take a look at some examples. So if we have y is equal to x squared plus 1, dy by dx is equal to 2x. If we have y is equal to x squared plus 3, dy by dx is also equal to 2x. If we have y is equal to x squared plus 5, again dy by dx is equal to 2x. So it follows that y equals x squared plus c, the derivative dy by dx is equal to 2x. So now let's look at the notation we use when integrating. So the integral symbol is an elongated s. Next is the function we're trying to integrate, so f of x. And then dx means the direction in which we're integrating. So dx means we're integrating along the x-axis. So effectively we're slicing up the x-axis and summing up those tiny slices to find the area under our curve. A definite integral is when we integrate between 2 points on the x-axis. So we integrate from x is equal to a to x is equal to b. This is a definite integral. If we're integrating without these points, then it's known as an indefinite integral. When we're using a definite integral and we're using it to calculate an area under a curve, we're calculating the area between these 2 points a and b. One of the rules of integration is known as the power rule. This says if we want to integrate x to the power of n by dx, this is x to the power of n plus 1 divided by n plus 1 plus a constant c. Let's look at some examples of using the power rule. So let's say we want to integrate x to the power of 5 dx. This is equal to x to the power of 5 plus 1 divided by 5 plus 1 plus a constant c, which is equal to x to the power of 6 divided by 6 plus a constant c. Let's look at another example, the integral of x to the power of 7 dx. Using the power rule, that equals x to the power of 7 plus 1 divided by 7 plus 1 plus a constant c, which equals x to the power of 8 divided by 8 plus a constant c. Now let's look at a simple definite integral. Let's suppose we want to integrate the function 2x from 0 to 1 in the x direction. Let's first take a look at what this means graphically. On the right hand side you can see I've plotted the graph of y is equal to 2x. Now if we integrate the function 2x from x is equal to 0 to x is equal to 1, so from there to there, we effectively find the area under this graph denoted by this shaded area. So as this area is a triangle, we can calculate it using the following. Area is equal to half times the base times the height. This is equal to half. Now the base from 0 to 1 is just 1 and the height is 2. There's the height multiplied by 2. So the area in this case is 1. Now let's integrate it and see if we come up with the same answer. So we're going to integrate the function 2x from 0 to 1 in the x direction. So this is the same as saying 2 times the integral from 0 to 1 of x dx. This is 2 times x to the power of 1 plus 1 divided by 1 plus 1, because n in this case is 1. And as always, we have a constant c. This is equal to 2 times x squared divided by 2 plus the constant c, which is equal to x squared plus c. Now, as we're integrating from 0 to 1, this is written as x squared plus c from 0 to 1. Now, this is x squared plus c at the value of 1, and we subtract x squared plus c at the value of 0. So if we put these values of 1 and 0 into these expressions, we get 1 plus c, and if we put 0 into x squared, it's 0, so minus 0 minus c. The c's cancel out, and we're left with 1. So the area again is 1. So just using this simple case, we can show that integration finds the area under this graph. Integration by substitution, or U substitution, is a special method of integration when what we are trying to integrate is set up in a particular way. To use this method, we need to be able to write our integral in the form where we have the integral of an outside function f and an inside function g of x multiplied by the derivative of g of x dx. So when we have an integral in this form, we can then substitute a value of u for the function g of x. And then the derivative of u with respect to x is du by dx, which is equal to g prime x. And then du is equal to g prime x dx. And hence, we have it in the form of the integral of the outside function f of u du. So let's look at an example here. So we have the indefinite integral of 2x cos of x squared plus 3 dx. In this case, u, our inside function, is u equals x squared plus 3. If we differentiate u with respect to x, we get du by dx equal to 2x. So as you notice, we have 2x when we differentiated u with respect to x, and we also have 2x in our integral. So du is equal to 2x dx. So we now have the dx part 2. So now we can do our substitution. So now we have the integral of cos u, and 2x dx is equal to du. So if we now integrate cos u du, we get sine u. And now if we substitute our u value back into this, this becomes the sine of x squared plus 3. And that's plus a constant of integration. So now let's take a look at another example. We want to find the indefinite integral of 4x times x squared plus 5 to the power of 3 dx. So in this case, let's pick u is equal to x squared plus 5. So the derivative of u with respect to x, so du by dx, is equal to 2x. So du is equal to 2x dx. So if we look at our original integral, we've got a substitution for u, and then we're left with 4x dx. So here we've got 2x dx. So if we multiply both sides by 2, we get 2 du equal to 4x dx. So now we have it in the correct form. So let's do our substitution. So now we have the integral. So x squared plus 5 is u. We have u to the power of 3. And 4x dx is 2 du. That's multiplied by 2 du. So we have 2 times the integral of u to the power of 3 du. So now we can easily integrate this using the power rule. So we have 2 times u to the power of 3 plus 1, which is 4, divided by 3 plus 1, which is 4, plus the constant of integration. So this is u to the power of 4 divided by 2 plus the constant of integration. So if we now substitute back in for u, we have x squared plus 5, which is u, and this is now to the power of 4 divided by 2 plus the constant of integration. So let's try and perform the indefinite integral of 8x multiplied by the square root of 40 minus 2x squared dx. So let's pick u equals 40 minus 2x squared. So du by dx equal to minus 4x. So du is minus 4x dx. As you can see, we're looking for 8x dx, and we have minus 4x dx. And not to worry, we can multiply both sides by minus 2. So minus 2 du is equal to 8x dx. So now we have it in the format that we need. So let's perform our substitution. So we have the integral. If we substitute for u, we have u to the power of a half multiplied by 8x dx. That's multiplied by minus 2 du. We take the minus 2 outside of the integral sign. We have minus 2 and integral of u to the power of a half du. So if we use the power rule to integrate this, we have minus 2 u to the power of a half plus 1 divided by a half plus 1 plus the constant of integration. So this is equal to minus 2 times u to the power of 3 over 2 divided by 3 over 2 plus c. So this is equal to minus 2 times 2 over 3 times u to the power of 3 over 2 plus c, which is equal to minus 4 divided by 3 times u to the power of 3 divided by 2 plus c. So now if we substitute u back in, it becomes minus 4 over 3 times 40 minus 2x squared, the power of 3 over 2 plus c. So let's try this one. Let's find the indefinite integral of x cubed multiplied by e power of x the power of 4 dx. So in this case, let's pick u is equal to x to the power of 4. So u equals x to the power of 4. So du by dx is equal to 4x cubed. So du is equal to 4x cubed dx. So this is not quite in the format that we need. We have an x cubed dx, but here we've got 4x cubed dx. So if we divide both sides by 4, we have du divided by 4 is equal to x cubed dx. So now we have it in the format that we need. So now let's perform our substitutions. So we have the integral of, so substituting for u, we have e to the power of u, and substituting for x cubed dx, we have du divided by 4. So if we take 1 over 4 outside of the integral, we have 1 over 4 multiplied into the integral of eu du. So if we integrate that, we get e to the power of u divided by 4 plus a constant of integration. So if we substitute u back into this expression, we get e to the power of x to the power of 4 divided by 4 plus constant of integration. So now let's try and perform the indefinite integral of 3x squared divided by 2x cubed minus 1 to the power of a third dx. So in this case, let u equal 2x cubed minus 1. So du by dx equal to 6x squared. So du is 6x squared dx. As you can see, this is not quite in the right form. We have 3x squared dx. But that's no trouble because we can just divide both sides by 2. So du by 2 equal to 3x squared dx. Now we have it in the right form where we can substitute for u. So we have the integral. So substituting for u, we have 1 divided by u to the power of a third multiplied by, and substituting for 3x squared dx, we have a half du. So tidying this up a little bit, we have, take the half outside the integral sign, we have the integral of u to the power of a minus 1/3 du. So if we now integrate this, we have a half times, and using the power rule, we have u minus 1/3 plus 1 divided by minus 1/3 plus 1 plus a constant. This is equal to a half times u to the power of 2/3 divided by minus the third plus 1 is 2/3 plus constant. So this is a half multiplied by 3 over 2 multiplied by u to the power of 2/3 plus a constant. This is 3/4 u to the power of 2/3 plus a constant. So if we now substitute back in for u, we get this is 3/4 multiplied by, and u is 2x cubed minus 1. So 2x cubed minus 1 to the power of 2/3 plus a constant. Integration by parts is a special method of integration often used when two functions are multiplied together. An example of this would be find the indefinite integral of x cos x dx. Integration by parts says the integral of u dv is equal to u times v minus the integral of v du. So we have x cos x dx. So we need to first find a u and a dv. So let's pick u to be equal to x and dv is equal to cos x dx. So if u is equal to x, as in this case here, du by dx, the derivative of u with respect to x, is 1. And therefore du is equal to dx. So we know that dv by dx is equal to cos x here. So therefore it follows that v is equal to the integral cos x dx. The v in this case is equal to sin x. So now let's put these values into our formula. So we have the integral of x cos x dx is equal to, so it's u, which we know is x, multiplied by v, which is sine of x, minus the integral of v, which is sine x, and du is just dx. So this is equal to x sine x minus, and then the integral of sine x dx is minus cos x. So this is equal to x sine x, minus and a minus make a plus, plus cos x, and then plus c, constant of integration. So let's look at another example now. Let's try and integrate the log of x divided by x squared dx. So using integration by parts, the integral of u dv is equal to uv minus the integral of v du. So let's pick u equals log of x and dv is whatever's left, so dx divided by x squared. So the derivative of u with respect to x, so du by dx is equal to 1 over x, and so du is equal to 1 over x dx. We now need to find v. Now we know that dv dx from here is 1 over x squared, so v is the integral of 1 over x squared dx. So using the power rule, this is equal to the integral of x to the power of minus 2 dx. That is equal to x to the minus 2 plus 1 divided by minus 2 plus 1, which is equal to x to the minus 1 divided by minus 1, which is equal to minus 1 over x. So this gives us u is equal to log of x, du is 1 over x dx, and v is equal to minus 1 over x. So the integral of log of x over x squared dx is equal to, the u is log of x times v, which is minus 1 over x. So that's minus log of x over x. So that's minus the integral of v, which is minus 1 over x, du, which is 1 over x dx. So multiplying those two together gives us minus 1 over x squared dx. So this is equal to minus log x divided by x. And if we take the negative sign outside of the integral sign, it becomes a plus, plus the integral x to the power of minus 2 dx. So that's equal to minus log x over x plus, now we can use the power rule to resolve this integral. So this is plus x to the power of minus 2 plus 1 divided by minus 2 plus 1. So this is equal to minus log x divided by x plus So the numerator, it becomes x to the power of minus 1, and the denominator becomes minus 1. That's minus 1 over x. So if we simplify this, it becomes taking minus 1 over x outside of the bracket, minus 1 over x multiplied into log of x plus 1, and let's not forget the constant of integration plus c. Now if we look at integrating e to the power of x times x dx, we can again use integration by parts, which is the integral of u dv equals uv minus the integral of v du. So let's pick u. Let's say u is equal to x in this case, and let's say dv is equal to the rest of the expression, which is equal to e to the x dx. So du by dx, we differentiate it, we get 1. So du is equal to dx, and v is the integral of e to the x dx, which is equal to e to the x. So now the integral of e to the x times x dx is equal to u times v. So u is x and v is e to the power of x. So it's x times e to the power of x minus the integral of v du. So v is e to the x and du is dx. So this equals x times e to the x minus the integral of e to the x, which is simply e to the x. So minus e to the x plus the constant of integration, which is equal to e to the x into the bracket of x minus 1 plus c. So let's use integration by parts to integrate e to the power of x times sine x dx. So in this case, let u equal sine x. So du by dx equal to cos x, and du is cos x dx. So dv is equal to e to the x dx. So v is the integral of e to the x dx, which is e to the x. So using integration by parts, the integral of e to the power of x sine x dx is equal to u times v, that's e to the power of x, times sine x, minus the integral of v, which is e to the x, multiplied by du, which is cos x dx. That's minus ex cos x dx. So it seems as though we haven't got too far with this, because we now have another couple of functions multiplied together. So we have e to the power of x multiplied by cos x dx, which we need to integrate. So let's persist with it and use integration by parts to perform this integral. We're going to try and integrate e to the power of x times cos x dx. This time let's pick u equal to cos x. So du by dx equal to minus sine x. So du is equal to minus sine x dx. dv is equal to e to the x dx. So v equals the integral of e to the x dx, which is equal to e to the x. So if we now put this all together, u times v is e to the power of x times cos x minus the integral of v du. So v is e to the x, du is minus sine x dx. That's minus minus, so we'll make this a plus, e to the x sine x dx. So now this integral looks very much like the one we started with. So let's see what we've got now. So the original integral, e to the x sine x dx equal to this part here, e to the x multiplied by sine x, minus the integral of this, which we know is this. So it's minus this, e to the x cos x, plus the integral of e to the x sine x dx. So now if we expand this, we have e to the x sine x minus e to the x cos x minus the integral of e to the x sine x dx. So now if we take this minus integral of e to the x sine x dx across the equal sign, we can combine it with what's on the left hand side. So we then have 2 into the integral of e to the x sine x dx is equal to, and we'll take e to the x and e to the x outside a bracket. So e to the x multiplied into sine x minus cos x. Therefore, our integral of e to the x sine x dx is equal to e to the power of x divided by 2 multiplied into the bracket of sine x minus cos x plus the constant of integration. So when using integration by parts, we need to pick a u value. So as a rule of thumb, try and choose u as follows. So pick inverse trig functions such as inverse sine 2, pick log functions 3, pick algebraic functions 4, pick trig functions, and 5, pick exponential functions. The expression we are trying to integrate is an algebraic fraction, and the algebraic fraction cannot be integrated using techniques like u substitution, etc. Then we need to break it into smaller expressions in order to integrate. The smaller expressions are known as partial fraction decomposition. We can use partial fraction decomposition if the degree of the numerator is strictly less than the degree of the denominator. To better explain this, let's look at an example. We want to find the indefinite integral of 2x minus 5 divided by 4x squared plus 7x minus 2. Note that the degree of the numerator is less than the degree of the denominator. Firstly, let's factorize the denominator and write the expression as follows. So it's the integral 2x minus 5 divided by 4x minus 1 multiplied by x plus 2 dx. Now let's first look at the expression and see if we can perform partial fraction decomposition and get it into the form of a divided by 4x minus 1 plus b divided by x plus 2. So if we write this as one fraction, we get a common denominator of 4x minus 1 multiplied by x plus 2, and the numerator is simply a multiplied by x plus 2 plus b multiplied by 4x minus 1. So if we multiply out the numerator, we get ax plus 2a plus 4bx minus b, and that's all divided by 4x minus 1 multiplied by x plus 2. So in the numerator, if we group our x terms together, we get x multiplied into a plus 4b minus b minus 2a, and that's all divided by 4x minus 1 multiplied by x plus 2. Now if we look at the numerator of the original expression we were trying to integrate, the numerator is 2x minus 5. So the coefficient here of 2 is equivalent to the coefficient down here of a plus 4b. So we can say that a plus 4b is equal to 2. Again, looking at the original expression, we have in the numerator 2x minus 5. The minus 5 here is equivalent to the minus b minus 2a here. So we can say minus 2a plus b is equal to 5. So I have equation 1 and equation 2. We multiply equation 1 by 2 and then add the equations. We get 9b is equal to 9. So in this case, b is equal to 1. And if we substitute the value of b equals 1 into equation 2, we have minus 2a plus 1 equals 5. So a equals minus 2. So now replacing a and b in our partial fraction decomposition, we now want to integrate minus 2 divided by 4x minus 1 dx plus the integral of 1 divided by x plus 2 dx. So using u substitution, let's integrate these two expressions. So in the first expression, let u equal 4x minus 1. And in the second, let u equal x plus 2. So du divided by 2 is 2 dx, and du is equal to dx in the second. And now let's substitute for u in the integrals. We have minus a half, and we want to integrate 1 over u du plus the integral of 1 over u du. So if we integrate this, we get the log of u minus half the log of u. So substituting back in for u in both these expressions, we get log of x plus 2 minus a half times the log of 4x minus 1, and that's plus the constant of integration. In part 2 of integration by partial fractions, we're going to look at a more complex problem with a polynomial of order 2 in the numerator and one of 3 in the denominator. The algebraic fraction here is difficult to integrate, so we must break it into smaller expressions in order to integrate. This technique is known as partial fraction decomposition. We can use partial fraction decomposition if the degree of the numerator is strictly less than the degree of the denominator. To better explain this, let's look at an example. We're going to try and find the indefinite integral of the expression shown on the board. Note that the polynomial in the numerator has a degree of 2 and the polynomial in the denominator has a degree of 3. And so this is suitable for partial fraction decomposition. Let's begin by factorizing the denominator. So leaving the numerator as it is, we have a denominator of x multiplied by 2x minus 1, which is again multiplied by x plus 2. Now let's look at the whole expression and get it into the form of a divided by x plus b divided by 2x minus 1 plus c divided by x plus 2. In order to do this, we need to work out what a, b, and c are. Treating this expression as 3 separate fractions that we want to add, we can now place them over a common denominator. If we now expand the numerator, we get the following expression. The next stage is to group the x squared, x, and constant terms together in the numerator. If we do this, we see that the x squared and x term have coefficients comprising of a, b, and c, and the constant term is minus 2a. The denominator remains unchanged. I've now removed the coefficients and constant from the numerator of this new expression and compared them with the original expression. As both expressions have only an x squared, x, and constant term in the numerator, and the denominator reaches the same, we can equate the coefficient of each and solve for a, b, and c. We could use Cramer's rule or Gaussian elimination to solve this set of equations. If you don't know how, please review my videos on these topics. In this case, however, it's more straightforward, as equation 3 has only one of the variables, so we can solve for a. So solving for a equals 1/2. If we now substitute for a equals a half in equation 1 and 2, equation 1 becomes b plus 2c equals 0, and equation 2 becomes 2b minus c equals a half. Now multiplying equation 2 by 2 and then adding the equations, we can eliminate c. This leaves 5b plus 0 equals 1 and allows us to solve for b, which in this case is 1/5. Now, substituting 1/5 for b in equation 1 allows us to solve for c. So we have 1/5 plus 2c is equal to 0, and therefore c is equal to minus 1/10. So now we have a is equal to half, b is equal to 1/5, and c is equal to minus 1/10. So now we've solved for a, b, and c. We can now substitute these values back into the original expression. This now transforms our original integral into 3 integrals, which are much more easily managed. So we're left with 1/2 multiplied by the integral of 1 over x dx, 1/5 multiplied by the integral of 1 over 2x minus 1 dx, and minus 1/10 multiplied by 1 over x plus 2 dx. Integrating these one by one, we can start with 1/2 times the integral of 1 over x dx. The integral of 1 over x dx is log of the absolute value of x plus the constant of integration. So we end up with 1/2 times the log of the absolute value of x plus the constant of integration. For the second integral, 1/5 times 1 over 2x minus 1 dx, we need to use u substitution. So if we start by letting u is equal to 2x minus 1, and then the derivative of u with respect to x is 2, so dx is equal to 1/2 du. Substituting these values in for x, we get 1/10 times the integral of 1 divided by u du, which equals 1/10 times the log of the absolute value of u plus the constant of integration. If we now substitute back in for u, we're left with 1/10 multiplied by the log the absolute value of 2x minus 1 plus a constant of integration. And for the last integral, we need to evaluate minus 1/10 times the integral of 1 over x plus 2 dx. So again, using u substitution, we let u equal x plus 2. du by dx, the derivative of u with respect to x, is equal to 1, and therefore du is equal to dx. If we now substitute our value of u in for x, we have minus 1/10 times the integral of 1 over u du. So evaluating the integral, we have minus 1/10 times the log of the absolute value of u plus a constant of integration. And now if we substitute back in for u, where u is equal to x plus 2, we're left with minus 1/10 times the log of the absolute value of x plus 2 plus a constant of integration. So our final solution is 1/2 times the log of the absolute value of x plus 1/10 times the log of the absolute value of 2x minus 1 minus 1/10 times the log of the absolute value of x plus 2 plus a constant of integration. Now we know that the area of a circle denoted by A is equal to pi r squared. How do we prove that this is true? We're going to try and prove this using integration. So let's start with the equation of a circle, which is y squared plus x squared equal to r squared. Let's rearrange this equation to get it in terms of y. So if we start with y squared is equal to r squared minus x squared, then y is equal to plus or minus square root of r squared minus x squared. So in this case, the negative square root of r squared minus x squared refers to the lower hemisphere of the circle, so this bit here, while the positive square root of r squared minus x squared refers to the upper hemisphere here. So let's look at finding the area of a quarter of this circle, so let's say here, and then multiplying the result by 4 to get the full area of the circle. So the area would equal 4 times the integral from 0 to r, the square root r squared minus x squared dx. So to work this one out, we need to do a substitute for x. So let x equal r sine theta. So dx d theta is equal to r cos theta, and dx is equal to r cos theta d theta. So using this substitution, the area of the circle can be written as 4 times the integral from theta equals 0 to theta equals pi divided by 2. So from 0 to 90 degrees. So theta is from here all the way through to here, pi by 2 radians. Now if we do our substitution, the square root of r squared minus, now x is equal to r sine theta. So x squared is r squared sine squared theta. And if we substitute for dx, that's r cos theta d theta. So r cos theta d theta. So now if we look at what's under the square root sign in isolation, the square root of r squared minus r squared sine squared theta, this is equal to r squared into 1 minus sine squared theta. Now fortunately there's a trig identity that'll help us out here. So we have the trig identity cos squared theta plus sine squared theta equal to 1. The cos squared theta is equal to 1 minus sine squared theta. So the square root can now be written as square root of r squared multiplied by cos squared theta. So now our area looks like this. Area is equal to 4 times the integral of theta equals 0, theta equals pi by 2, the square root of r squared cos squared theta multiplied by r cos theta d theta. So now if we take the square root of this, the area is equal to 4 times the integral from theta equals 0, theta is pi by 2 of r cos theta multiplied by r cos theta d theta. So the area is, so we have r squared again, which we can take outside the integral. So we now have 4r squared, and then we have the integral of theta equals 0, theta is pi by 2 of cos squared theta d theta. Now to integrate this, we can use another trig function. Cos squared theta is equal to a half multiplied into 1 plus cos 2 theta. So if we substitute this into our area equation, we have the area is now equal to, we take the half outside the integral sign and divide it into 4r squared. We get area is equal to 2r squared. And then the integral from theta equals 0, theta equals pi by 2 of 1 plus cos 2 theta d theta. Our area can now be written as follows. So the area of the circle is 2r squared multiplied by the integral from 0 theta is 0 to theta is pi by 2 of 1 d theta plus 2r squared multiplied into the integral from theta is equal to 0 theta is equal to pi by 2 of cos 2 theta d theta. So now if we look at the second integral in isolation, we want to integrate cos 2 theta d theta. So if we make some substitutions here, so if we say let u equal 2 theta, and then we have the derivative du by d theta equal to 2, and d theta is equal to du over 2. So if we substitute these values into our original integral, we have the integral of cos u, and d theta is du over 2. If we take the half outside the integral, we have a half du. So the integral of this is a half sine u plus c. So if we substitute our u value back into this, it's a half sine 2 theta plus c. Our area is now a equals, we take the 2r squared out, the 2r squared, and then we have the integral of 1 d theta is just theta plus the integral of cos 2 theta, which is a half sine 2 theta, and it's from theta is 0 to theta is pi by 2. So if we now evaluate this from 0 to pi by 2, we have our area equal to 2r squared multiplied into, and then we have substituting pi by 2 in, we have pi by 2 plus a half times the sine of, so if we substitute pi by 2 into 2 theta, we get sine of pi, and this is a big minus. We substitute 0 in now, we get 0 for theta plus a half sine of 0. So our area is equal to 2r squared. So looking at the first expression, we have pi by 2 plus a half times the sine of pi. Now the sine of pi is 0, so the whole thing becomes 0, minus 0 plus. So the sine of 0 is 0, multiplied by a half is also 0. That leaves us with the area is equal to 2r squared, pi divided by 2 minus 0, and that is equal to 2r squared multiplied by pi divided by 2. 2's cancel out, and our area is equal to pi r squared. On the left hand side of the board, I've drawn a cone. The height of the cone is h on the x-axis, and if we start at x equals h and work towards x equals 0, we can think of this cone as a series of ever decreasing circles about this line here. The largest of the circles, or the base of the cone, has a radius of r. To find the radius of all other circles within the cone, we need to find the equation of this line. So to help explain this, I've drawn this line on a separate graph. On the graph, I've indicated point h on the x-axis and point r on the y-axis. H is the height of the cone, and r is the radius of the circle at the base of the cone. So the equation of this line is given by y is equal to mx plus c, where m is the gradient and c is a constant. So the gradient m is given by the rise divided by the run. So the rise in this case is r and the run is h. So rise divided by run is r divided by h. So the equation of this line is y is equal to rx divided by h plus c, which is 0. So y is equal to rx divided by h. So at any point on the x-axis within the cone, we can find the radius of any of the circles. Let's test this out by finding the radius at the base of the cone. So we know the equation of the line is y equals r over h multiplied by x. And at the base of the cone, we know that the x value is h. So y is equal to r divided by h multiplied by h. So the radius at the base of the cone, which we know is r. So we know that this now works and is true. So now if we add up the areas of all these circles from x equals 0 to x equals h, we'll get the volume of the cone. So the area of any one of these circles, as we know, is area is equal to pi r squared. So now if we sum the area of all these circles, we can integrate from x equals 0 to x equals h. So we're integrating in this direction, and we integrate pi multiplied by, now the radius of any one of these circles, as we've already seen, is r divided by h x squared. And as we're integrating in the x direction, so each infinitesimal circle, we need dx. If we now take all the constants outside of the integral, this becomes pi r squared over h squared into the integral from 0 to h of x squared dx. If we now integrate this using the power rule, we get the volume of our cone is equal to pi r squared over h squared multiplied into x cubed over 3 from 0 to h, and that equals pi r squared over h squared multiplied by h cubed over 3 minus 0, and that is pi r squared h over 3. So that proves that the volume of our cone is pi r squared h over 3. If we take a sphere in 2 dimensions and place it on an xy axis, it looks like a circle with radius r. The sphere is made up of an infinitesimal number of circles within. Here are some that I've drawn on the diagram. The radius of each of the circles, as shown here, is equal to y, as that's the distance from the x-axis to the point at which it reaches the sphere. Now we know the area of a circle is given by pi r squared, where r is the radius of the circle. So for each of our internal circles, the area can be given by pi y squared, as we've determined that y is the radius of each of the internal circles. So if we now express this in terms of the radius r of the sphere, as this radius doesn't change, we can do this by creating a triangle here. It's a right angle triangle, and the hypotenuse side is given as r, the radius of the sphere, and we have a side of y and a side of x. So if we use Pythagoras' theorem, we have y squared plus x squared is equal to r squared. So y squared is equal to r squared minus x squared, and therefore y is equal to plus or minus the square root of r squared minus x squared. If we now substitute for y in the area formula, we get the area is equal to pi times the square root of r squared minus x squared squared, which equals pi times r squared minus x squared. Now to get the volume of the sphere, we need to sum up all these circles. We do that by integrating. So the volume of the sphere, V, is the integral from x equals minus r to x equals r of pi multiplied into r squared minus x squared by dx. If we now work out this integral, let's first remove pi outside the integral to give pi into the integral from minus r to r of r squared minus x squared dx. If we integrate this, we get pi into integrating r squared, we get x r squared minus, and the integral of x squared is x cubed divided by 3, and that's from minus r to r. So when we put our values of r and minus r in, we get our volume is equal to, so plugging in r, we get r cubed minus r cubed divided by 3 and that's multiplied by pi, of course, minus pi multiplied into, and if we put our negative r in, we get minus r cubed minus r cubed divided by 3. So this gives us 2 pi r cubed divided by 3 minus pi multiplied into minus r cubed plus r cubed divided by 3, which in turn gives us 2 pi r cubed divided by 3 minus pi multiplied by minus 2/3 r cubed. So this gives us 2 pi r cubed over 3 plus 2 pi r cubed over 3, which is equal to 4/3 pi r cubed, which is equal to the volume of a sphere. Here we have an x-y axis. If we take this line, which cuts the y-axis at point R, and spin it around the x-axis, it creates a cylinder. The equation of this line is y is equal to r. This means that for any value of x, the y value is going to be a constant, which in this case is r. If we think of this cylindrical shape that's been created as being a bunch of infinitesimal number of circles, which I've shown in different colors along the cylinder, then to find the volume of the cylinder, we need to sum up the area of each of these circles. We do that over a distance of h on the x-axis, which is the height of the cylinder in this case. If the area of each of the circle slices that make up the cylinder is equal to pi r squared, the volume of the cylinder, V, is equal to the sum of the area of all the circle slices. So to find this, we need to integrate pi r squared along the x-axis, so dx, from 0 on the x-axis to h on the x-axis, which represents the height of the cylinder. If we now evaluate this integral, the volume of the cylinder is equal to pi r squared x, obtained using the power rule using integration, and that is from 0 to h. So the volume of the cylinder is equal to pi r squared, and substituting h in for x, minus pi r squared, and if we put 0 in for x, we get the volume equal to pi r squared h. So that's the volume of the cylinder derived using integration. Let's look at how we find the area between two curves given only the equation of each curve. The diagram of the board shows two curves, and the red shaded region is the area we want to calculate. The equation of each curve is shown. We have y equals minus x squared plus 2 and y equals x squared. The first step in finding the area of the red region is to find the x coordinates of where the two curves intersect. To do this, we can equate the two equations and find the values of x at the points of intersection. Equating the two equations gives x squared is equal to minus x squared plus 2. Adding x squared to both sides of the equation gives 2x squared is equal to 2. Dividing both sides of the equation by 2 gives x squared is equal to 1. It follows that x is equal to plus or minus the square root of 1, and therefore x is equal to plus or minus 1. Now let's look at each of the curves in turn between the limits of x equals minus 1 and x equals 1. So for y equals minus x squared plus 2, the area between x equals minus 1 and x equals 1 and under the curve is shown by the blue shaded region. And for y equals x squared, the area between x equals minus 1 and x equals 1 and under the curve is shown by the green shaded region. If we now subtract the area of the green shaded region from the area of the blue shaded region, we'll find the area between the curves shown by the red shaded region. So let's start by finding the area of the blue shaded region. To do this, we can integrate the function y equals minus x squared plus 2 between the limits of x equals minus 1 and x equals 1. The antiderivative of this is minus x cubed divided by 3 plus 2x, and we need to evaluate this between x equals minus 1 and x equals 1. If we now plug the limits of integration into the antiderivative, we have minus 1/3 plus 2 and minus into the bracket of 1/3 minus 2. And evaluating this gives 10 divided by 3. And similarly, to find the area shaded in green, we can integrate the function y equals x squared between x equals minus 1 and x equals 1. The antiderivative of this is x cubed divided by 3, which we need to evaluate between x equals minus 1 and x equals 1. And plug in the limits of integration into the antiderivative, we have 1/3 minus 1/3, which is equal to 2/3. And so the area of the red shaded region is the area of the blue shaded region, which we've calculated as 10 divided by 3, minus the area of the green shaded region, which we've calculated as 2/3. And so the area of the red shaded region is equal to 8 divided by 3, and this is our final answer. Let's look at how we find the area between two curves, where one curve is below and the other above the x-axis. The diagram on the board shows two curves, and the red shaded region is the area we want to calculate. The equation of each curve is shown. We have the curve above the x-axis as y equals x cubed plus 1, and the curve below the x-axis we have as y equals x cubed minus 2. And for this example, we're going to find the area between the interval x equals 0 and x equals 1. Let's now look at each of the curves between the limits of x equals 0 and x equals 1. So for y equals x cubed plus 1, the area between the limits of x equals 0 and x equals 1 and under the curve is shown by the blue shaded region. And for y equals x cubed minus 2, the area between x equals 0 and x equals 1 and under the curve is shown by the green shaded region. If we now subtract the green shaded region from the blue shaded region, we find the area between the curves shown in red. I can now hear you scream, "How can this possibly be true, John?" And understandably so, as this is not intuitive. So let's take a look at why this is so. The area of the blue shaded region is a positive value, as the area is above the x-axis, and the area of the green shaded region is a negative value, as the area is below the x-axis. So subtracting the green shaded region from the blue shaded region effectively adds the two areas together, as two negatives make a positive. Now, to find the area of the blue shaded region, we can integrate the function y equals x cubed plus 1 between the limits of x equals 0 and x equals 1. Using the power rule to evaluate this, we get x to the power of 4 divided by 4 plus x, and we need to evaluate this between 0 and 1. So if we plug in these limits, we get 1/4 plus 1 minus 0, and this evaluates to 5/4. And similarly, to find the area of the green shaded region, we can integrate the function y equals x cubed minus 2 between the limits of x equals 0 and x equals 1. And using the power rule, this evaluates to x to the power of 4 divided by 4 minus 2x. And plugging in the limits of 1 and 0, we have 1/4 minus 2 minus 0, which equates to minus 7/4. So now, the area of the red shaded region is the area of the green shaded region, which evaluates to negative 7/4, subtracted from the area of the blue shaded region, which evaluates to positive 5/4. So we have 5/4 minus 7/4, which gives us 12/4, and therefore the area of the red shaded region is 3 units squared. Let's look at how we find the area between two curves where both curves are below the x-axis. The diagram on the board shows two curves, and the red shaded region is the area we want to calculate. The equation of each curve is shown. We have y equals x cubed minus 2 and y equals x cubed minus 4. And for this example, we're going to find the area between the interval x equals 0 and x equals 1. Let's now look at each of the curves between the interval of x equals 0 and x equals 1. So for y equals x cubed minus 2, the area between the interval and under the curve is shown by the blue shaded region. And for y equals x cubed minus 4, the area between the interval and under the curve is shown by the green shaded region. If we now subtract the green shaded region from the blue shaded region, we find the area between the curves shown in red. I can now hear you scream, "How can this possibly be true, John?" And understandably so, as this is not intuitive. So let's take a look at why this is so. When we integrate to find the area of the green shaded region is a negative value. This is because the area is below the x-axis. And similarly, the area of the blue shaded region is also a negative value. And so subtracting the green shaded region from the blue shaded region effectively adds a positive value to a negative value, as two negatives make a positive. It's important here that we subtract the largest of the negative values from the smallest. So which is the largest and which is the smallest? The largest negative value belongs to the curve furthest from the x-axis, or the bottom curve, so where y is equal to x cubed minus 4. And the top curve, so where y is equal to x cubed minus 2, is the smallest negative value. If we now integrate the function x cubed minus 2 across the interval x equals 0 to x equals 1, we'll find the area of the blue shaded region. So using the power rule to evaluate this, we have x to the power of 4 divided by 4 minus 2x. And if we plug in the limits of integration of 1 and 0, we get a quarter minus 2 minus 0, which equals minus 7 over 4. And if we integrate the function x cubed minus 4 between the limits of x equals 0 and x equals 1, we find the area of the green shaded region. Using the power rule to evaluate this integral, we have x to the power of 4 divided by 4 minus 4x. And plugging in the limits of integration for this, we have a quarter minus 4 minus 0, which equates to minus 15 over 4. And if we subtract negative 15 over 4 from negative 7 over 4, we get the area of the red shaded region, which in this case is 2. In a previous video, we looked at how we calculate the area under a curve using integration. We looked at a function y is equal to f of x, and we summed infinitely small slices under the curve along the x-axis. Each of the slices was of width dx. We did this by integrating along the x-axis, and in this case on the left, from a to b. This gave us the area under the curve over the range a to b. And as you can see, this area is shaded in green in the diagram on the left. Now we want to take this a step further, and we can use integration to calculate the volume under a curved surface. Our surface is a function of both y and x. So in our diagram on the left, we now have a new axis, z or z, depending where you come from. And z is a function of x and y. So what this means is if I plug in values for x and y into this function, it will give me values of z, which will equate to points on the pink surface shown. So effectively, this gives us the height of the shape. I've now marked points A and B on the x and y axis. These points form a rectangular shape in the xy plane. If I extend the lines up to meet the curved surface, as I've done in the diagram, then the volume now enclosed by this and under the curved surface is the volume which we're attempting to find. If we now take a fixed point on the y-axis, shown as C on the diagram, how would we go about calculating the area shaded in blue? We know that our function is given by f of xy. So each change in the value of x would give a different value of z. If we now take a tiny slice along the x-axis, so dx, this will give us a tiny slice of the area of the blue shaded region. If we add up all these tiny slices of area, we get the total area defined by the blue shaded area. We do this by integrating our function f of xy from 0 to a by dx. So that's along the x-axis. Once we've done this, it'll produce a function of y. If we then plug in different values of y along the y-axis, this will generate different slices of area. So now if we take a slice of area and multiply it by a small change in y, so dy, we get a small slice of volume under the surface. I've shown this on the diagram on the left. If we then sum the small slices of volume across the y-axis, we get the total volume under the curved surface. Again, we do this by integration. So we've already integrated to get a small slice of area shown previously. We integrated along the x-axis from 0 to a of our function f of xy by dx. This gave us a small slice of area. If we now integrate along the y-axis from 0 to b, so we take the integral from 0 to b of the integral from 0 to a of f of xy dx by dy, we will get the total volume under the surface. It's not important whether we integrate along the x or y-axis first. Either way, we could achieve the same results. So in the diagram, I've integrated along the x-axis first from 0 to b. So I've taken the integral of 0 to b of our function f of xy by dy. This will give me a slice of area shown by the blue shaded area. If I then integrate from 0 to a along the x-axis, this will add up all those slices of area to give me the total volume under the curved surface indicated by the pink area. Now let's look at a real example. On the left, there's a surface which maps to the function z is equal to x times y squared. We want to find the area beneath the surface between the points 1 and 5 on the x-axis and 0 and 2 on the y-axis. So we want to integrate xy squared from 1 to 5 across the x-axis and then integrate again from 0 to 2 across the y-axis. So let's first do the x integral. So we're going to integrate from 1 to 5 xy squared dx. So in this case, the y term is a constant, and the integral should give us a function of y as we saw in the presentation. So if we integrate x, we get x squared over 2 times y squared, a values of x between 1 and 5. So if we put our value of 5 in for x, this gives us 25 divided by 2 y squared minus, now if we put our value for x equal to be 1, it becomes minus a half y squared. And if we subtract those two fractions, we get 24 divided by 2 y squared, which is equal to 12 y squared. So this will give us a slice of area under the curve for any value of y. So now we want to integrate in the y direction from 0 to 2 of 12y squared dy. So this will allow us to add up the slices of volume in the y direction and eventually give us the volume under the surface. So if we integrate this, it gives us 12y cubed divided by 3. And we want that between y is equal to 0 and y is equal to 2. So this is 4y cubed from 0 to 2. So if we plug these values in, we put 2 in, we get 4 times 2 cubed is 8. And if we put the 0 value in, we just get 0. So this gives us a value of 32, which is our volume under the curved surface. between the values of x is 1 and x is 5 and y is 0 and y is 2. Now during the presentation I said we could do the integral across the x-axis first or the integral across the y-axis first. So let's demonstrate that we can actually do that. So this time we want to integrate from 0 to 2 xy squared dy, and then we want to integrate from 1 to 5 the result of this function, which will be a function of x, by dx, so along the x-axis. So let's integrate along the y-axis first. So from 0 to 2 xy squared dy, we integrate this, we get xy cubed divided by 3 from 0 to 2. So if we plug in the value of 2 for y, we get 2 cubed, which is 8, multiplied by x divided by 3. And if we plug in the value of 0, we get 0. So we're left with a function 8x over 3. Now we want to integrate that. So we integrate from 1 to 5, 8x divided by 3 along the x-axis. So if we do that, we get 8x squared divided by 3 times 2. And that's from the values of 1 to 5. So that equals 4 divided by 3 x squared between the values of 1 and 5. So if we plug the value of 5 in for x, we get 4 times an x squared. So 5 squared is 25 divided by 3. And we want to subtract the value when we put 1 in for x. So that leaves 4 divided by 3. So if we take the 4/3 out of this expression, we get 4/3 multiplied into 25 minus 1, which is equal to 4 times 24 divided by 3, which gives 3 into 24 goes 8 times. So 4 times 8 gives us 32, which is the same answer as we had when we integrated along the x-axis first. Let's say we want to find the volume of a rectangular cuboid. Then a simple way of doing this would be to multiply its length, width, and height together, as these would be constants. Well, imagine an irregular shape where the length, width, and height are no longer constant and are given by a function. How would we go about finding its volume? I want to show you a way that we can do this. So let's start with our regular shape, where we have a length along the x-axis of 4, a width along the y-axis of 3, and a height along the z-axis of 5. We all know that the volume is given by the length multiplied by the width multiplied by the height. So in this case, the volume is 4 multiplied by 3 multiplied by 5, which is 60. Now let's imagine our rectangular cuboid shape is made up of infinitesimally small rectangular cuboids, so small that they're only visible under a microscope. For visual purposes here, I've magnified these in the diagram. Now let's take one of these infinitesimally small rectangular cuboids and look at its dimensions. So the length along the x-axis is a tiny chunk of the total length of 4, and we'll refer to it as dx. The width along the y-axis is a tiny chunk of the total width of 3, and we'll refer to it as dy. The height along the z-axis is a tiny chunk of the total height of 5, and we'll refer to it as dz. Now, if we multiply dx by dy by dz, we get a tiny chunk of volume, which we call dv. If we sum all the tiny pieces of volume, we arrive at the total volume of our rectangular cuboid. So how do we do this, John, I hear you cry? Well, we use 3 integrals to sum along the x, y, and z axis. And this is how we find the volume of irregular shapes. We break the total volume up into rectangular cuboids and sum the rectangular cuboids. And the challenging part is defining the region, which relates to the limits of integration. When we are dealing with a regular shape, the limits of integration are constant and therefore straightforward. However, with an irregular shape, the limits of integration are not constant and require some thought. So let's apply this to our rectangular cuboid and verify that we get a volume of 60 cubic units, as we did when using the volume formula. The total volume is given by these three integrals. There are a number of different ways of writing it, and I've shown two ways of doing this on the board. The outer integral is the height component, and it's from z equals 0, the origin, to z equals 5, so 5 units along the z-axis, and we're integrating dz. The middle integral is the width component, and it's from y equals 0, so the origin, to y equals 3, so 3 units along the y-axis, and we're integrating dy. And the inner integral is the length component, and is from x equals 0, so the origin, to x equals 4, so 4 units along the x-axis, and we're integrating dx. Let's now evaluate these integrals and calculate the total volume. So beginning with the height component, we want to integrate between z equals 0 and z equals 5 dz. And using the power rule to evaluate this integral, we get z. And plugging in the limits of integration, we have 5 minus 0, which equals 5. And for the width component, we want to integrate from y equals 0 to y equals 3 dy. So evaluating this using the power rule, we get y. And plugging in the limits of integration, we get 3 minus 0, which equals 3. And for the length component, we want to integrate from x equals 0 to x equals 4 dx. And evaluating this using the power rule, we get x. Plugging in the limits of integration, we get 4 minus 0, which equals 4. And multiplying all three results together gives us a total volume of 60 cubic units. Simpson's rule is a numerical method to approximate the solution of a definite integral. In some circumstances, we come across functions which cannot be evaluated using standard techniques. In these circumstances, we can use a numerical method which approximates the area under a curve between 2 points on the x-axis. So let's see how Simpson's rule works. I've sketched a continuous function f of x, which is defined across an interval of ab. Using this method, the area of the function is broken up into an even number of strips. A parabolic approximation of the area is done across pairs of strips, and the approximate area calculated for each pair is summed to give an approximation of the total area. The greater the number of pairs of strips, the better the approximation. In the sketch, I've chosen to use 2 pairs of strips, so 4 strips in total. Let's drill down into a pair of strips and take a look in more detail at how this works. I've extracted the blue shaded area, which contains 2 strips. Note we need 2 strips, as the formation of a parabola requires 3 data points. The parabola is an order 2 polynomial of the form shown here as f1 of x equals a0x squared plus b0x plus c0. The parabola is formed between the points shown here, here, and here. The dark green curve here represents its shape. The area under the parabola is calculated and used to calculate the total area. Each pair of strips will have an associated parabola. The areas under each parabola are summed to give an approximation of the area under the curve. Note that the more pairs of strips used, the better the approximation. The formula for Simpson's rule can be written as follows. H divided by 3 multiplied into the first height plus 4 times the sum of the odd heights plus 2 times the sum of the even heights plus the last height. Now let's work through the formula and see how it relates to the function f of x. Starting with h, this is the width of each of our intervals or strips as shown on the sketch, and is calculated by subtracting the start of the interval on the x-axis, a, from the end of the interval, b, and dividing this number by the number of strips we want to use. The number of strips we can call n. In our example, we have 4 strips, and note for this to work, the number of strips must be an even number. Note the start of the interval a on the x-axis is now marked as x0, and the end of the interval b on the x-axis is x4 or xn. The first height is the one shown here, which we call y0 and labelled as first. So it's the value of the function f at x0, which is the start of the interval, also labelled as a on the sketch. Next, we want to look at what is meant by odd heights in the equation. The point to the right of x0 on the x-axis is x1. Its corresponding height is y1, shown here. As the number 1 suggests, this is one of the odd heights, and I've marked it with an O. Its value y1 can be obtained by evaluating the function at x1. The other odd height in our example is y3, shown here and marked with an O. This height is obtained by evaluating the function at x3. Let's look at what is meant by even heights in the equation. y2 shown here and marked with an E is an even height, as the number suggests, and can be obtained by evaluating the function at x2. Finally, y4 in our example is the last height referred to in the equation of the Simpson's rule, shown here, and is also referred to as yn. It's obtained by evaluating the function at xn, or in this case, x4, which is the end of the defined interval. The general form of the equation can be written as h divided by 3 multiplied into the first height y0 plus 4 times the odd heights, which range from y1 to yn minus 1, plus 2 times the even heights, which range from y2 to yn minus 2, plus the last height yn. Now let's apply Simpson's rule to a real problem. So we want to use Simpson's rule with 4 strips to evaluate the integral from 0 to 2 of 2 to the power of x dx to 3 decimal places. So now let's take a look at the graph of y equals 2 to the power of x in Desmos. So as you can see, it has an interval from 0 to 2, and I've created 4 strips, or 2 pairs of 2. Each of the strips as a width of 0.5, and we'll see how we get that value when we go back to the whiteboard. I've sketched the graph of y equals 2 to the power of x on the whiteboard. I've split the curve up into 4 strips across the interval 0 to 2 as the question asks. I've also put up a reminder of Simpson's rule. First, let's work out what the value of h is. We have 4 strips, so n is 4. H is the start point on the interval, which is 0 in this case, subtracted from the end point, which is 2. And the result of this divided by n. So we have 2 minus 0 divided by n, which is 0.5. To help us evaluate this, I've created a table. This is filled in with what we already know. So looking at the first row, we have n. This goes from 0 to 4 in steps of 1. The column labelled xn is the x-coordinate of each step, beginning at our starting value of 0 and ending at 2, our end point. The values in between are incremented by h, which we've calculated as 0.5. The next column, yn, is the height that we need to calculate. These are calculated by evaluating the function at the x-coordinate shown. The next column is the multiply sign, which relates to the formula. So the first and last heights at x equals 0 and x equals 2 are multiplied by 1. The odd heights, so that's at x equals 0.5 and x equals 1.5, are multiplied by 4. And the even heights at x equals 1 is multiplied by 2. The last column is the height, or the value in column yn, multiplied by its multiplier. So starting with n equals 0, to get the missing value in the yn column, we need to evaluate the function 2 to the power of x at the value of 0. So that is 2 to the power of 0, which equals 1. So if we multiply 1 by 1, we get 1. Now looking at the second row of the table where n is equal to 1, we see that the x-coordinate is 0.5. So we need to evaluate the function at 0.5. So the function is 2 to the power of x. So x in this case is 0.5 or a half. So when we evaluate the function, we get 2 to the power of a half, or the square root of 2. Now, because this is an odd function, we need to multiply it by 4. So we have 4 times the square root of 2. So y1 is equal to 4 times the square root of 2. So now moving on to the third row, where n is equal to 2. We need to evaluate the function at x equals 1. This will give us our y2 value, which is an even value or an even height. So evaluating the function at x equals 1, we get 2 to the power of 1, which is equal to 2. And because it's an even height, we need to multiply this by 2. So we have 2 multiplied by 2, which gives us 4. And now moving on to the fourth row where n is equal to 3, we want to calculate the height y3. So to do this, we need to evaluate the function at 1.5. So x is equal to 1.5. So it's 2 to the power of 1.5, or 2 to the power of 3 divided by 2, which is equal to 2 multiplied by root 2. As this is an odd height, we need to multiply it by 4. So it's 2 root 2 by 4, which gives 8 times root 2. So looking at the last row where n is equal to 4, we need to evaluate the function at x is equal to 2. This will give us the height y4. So the function 2 to the power of x, where x is equal to 2, gives 2 to the power of 2, which is 4. Now this is the last height, so it doesn't have a multiplier, so we can multiply it by 1, and this will give us 4. If we now sum the last column shown here, we get a value of 25.9706. Multiplying this value by the value of h, which is 0.5 divided by 3, we get our final answer of 4.328.